I would like to introduce our work Pragh. It is a live migration scheme to preserve locality for graph traversal. It is a joint work with my colleague Xingda and my advisors Rong and Haibo. So graphs can model connect relationships among data and are widely used in many domains such as social network. And in graph system, traversal queries are key operations to support emerging applications such as user profiling. When executing traversal queries, it is important to preserve locality because local memory access are orders of magnitude faster than remote ones, even on fast network. To show this, let's look at an example query in social network, which finds the indirect follow-E of Haibo. To find the follow-E's, we start from Haibo's vertex and traverse a graph according to the friend edge. Graph is usually large, so the graph is randomly partitioned on 2 nodes and stored by key-value store. The vertices are keys and their neighbors are values. As we can see, the follow-E Rong is on the same node with Haibo, so we can directly fetch it using local access. However, the follow-E of Rong is on another node, which results in remote accesses. Meanwhile, it is challenging to preserve locality on dynamic workload, as traditional static partition scheme cannot handle different traversal workloads. For example, at 12 o'clock, a query about Haibo starts from node 0. After a while, another query about Xiating starts from node 1, which is competing with the first query. This is a false contention complicating static partition. So traditional storage systems use live migration to preserve locality. Once the workload changes, live migration moves data according to locality requirement. In the example, node 0 requires data of Rong. Live migration moves data, and now all the data are local. After a while, the workload changes, so the data of Rong is migrated back again. However, traditional shard-based migration does not fit graph traversal. This is because graph is schemaless and hard to partition related data into shard. For example, 2 key-value pairs are grouped and migrated in shard. A query about Haibo traverses from shard 2 to shard 0. Meanwhile, another query about Ning also reaches shard 0. 2 queries are competing for different data in the same shard, incurring false contention. This weakens effects of migration. What's worse, fine-grained shard partition suffers another problem of metadata. As shard's location is dynamic, metadata is necessary to maintain the latest location. For example, to find the follow-E of Rong, we first need to look up metadata and find shard 0 is on node 1. Then find the data. Notice that metadata is non-scalable as each node needs to cache entire metadata to speed up the query. To show the problem of shard-based migration, let's look at an evaluation on a representative traversal workload. The left y-axis is number of metadata entry, and the right y-axis is throughput. The x-axis is number of shards. The size of the shard is decreased. With coarse-grained shard, the fine-grained benefit is weak due to high false contention. The benefit becomes good only with fine-grained shard, which suffers heavy and non-scalable metadata overhead. So how to achieve zero metadata fine-grained migration on graph traversal? A hardware feature called RDMA is becoming popular recently to accelerate distributed applications. It provides cross-node accesses with high speed, low latency, and kernel bypassing. The one-sided primitive such as read, write, and compare and swap, allows direct access to another node by passing the host CPU. The primitive changes data access pattern. It splits accesses to keys and values, which opens an opportunity for zero metadata fine-grained migration. Let's see how RDMA splits accesses first. To get data of Rong on node 1, it first fetches the address of value with one RDMA read, and then use another read to get the value. In short, it requires two reads to fetch one key-value pair. RDMA makes it easy and efficient to split keys and values in physical. Suppose we only migrate value. After migration, the target first fetch key with remote access and then get value with local access. This improves performance by reducing remote value, and the migration granularity is in key-value pairs. Further, we notice that the location of key is not changed as the key is not migrated. So there's no need of metadata to maintain the latest location. In short, this achieves zero metadata fine-grained migration. Our system Pragh uses split live migration, which separately migrates values and does not migrate keys. This avoids remote values and it maximizes migration benefits using this zero metadata fine-grained migration. The evaluation shows the effectiveness. Beyond this, Pragh also supports other functions such as source bypassing migration, fully localized migration, lightweight fine-grained monitor, and migration on evolving graphs. Before we dig into Pragh's detail, let me briefly introduce Pragh's system model. Each server contains three components. The storage layer adopts an RDMA-friendly key-value store. The target and task engine handles requests from the clients by key-value operations. And Pragh adds a migration toolkit, which enables monitor to collect statics and migration threads to do live migration. And here is the outline of the remaining content. Due to time limit, I will introduce these three techniques. We start by unilateral migration protocol. It is important to prevent the source node from interruption, as the source node may be busy processing concurrent query. The unilateral migration protocol totally migrates data by the target. It leverages RDMA because RDMA primitives totally bypass the source CPU. Although RDMA is CPU bypassing, it is challenging to use it for migration due to its weak semantics. Pragh carefully rehearsals read, write, and compare and swap operations. In detail, it is a 5-step protocol to migrate value and update address in a key. First, the target allocates memory and then copies value by read. Third, since the key is not migrated, the address is remote for the target. Pragh uses atomic update by RDMA compare and swap, which can co-work with concurrent queries on the source. To make compare and swap work, the address is carefully encoded into 64 bits by hybrid encoding. Finally, the target releases remote memory. It adopts passive invalidation and list-based reclaim mechanisms. For more details, you can refer to the paper. This is the second technique. With split migration, the remote access is about half of the original. However, it is still far from optimal because Pragh uses additional remote access for the address. This is a common challenge for RDMA-based key-value store. Previous work uses a location cache to reduce remote key. In detail, with location cache, the target can get address of value locally and fetch value with one RDMA read. Our observation is that location cache is a perfect match for split migration. The key reason is that they avoid half of remote access respectively. Besides, they both want remote data access frequently. Based on this observation, we integrate split migration with location cache to avoid remote accesses. With cache, after migration, both key and value are local, so it is fully local access now. Although location cache avoids remote keys, it complicates consistency of migration. Finally, I will introduce lightweight monitor, which enables fast detection of migration requirements due to workload changes. The function of monitor is to collect access statics so that the coordinator can make migration plan. Pragh's fine-grained migration, though, maximizes benefits, making monitor challenging because the monitor should carry on per key granularity, which has non-trivial overhead on large graphs. Pragh uses a separate monitor to achieve lightweight fine-grained monitor. The observation is that migration may only care about the remote data frequently accessed. So Pragh only tracks the remote access reusing location cache. If necessary, monitor will check local access on demand. And there are some other techniques in Pragh. To show the effectiveness of Pragh, we did evaluation on micro benchmark on a cluster of 8 nodes. The ideal baseline is the throughput on one single node multiplied by 8, the number of nodes. And the shard-based migration has 800 shards in total. We noticed that the throughput before migration is far from the ideal one. Then we compare different migration schemes. Shard-based migration moves over 85% of data, but increases the throughput by only 40%, as the remote access rate is still 64%. Our split migration moves very few data. With the basic split migration, the throughput is improved by 90% since remote value is avoided. Split migration with location cache increases the throughput by 19 times and enriches 70% of the ideal one. This is because, this is because the this is because over 97% of remote access are reduced. And we also port Wukong to use Pragh, which is a graph store processing concurrent CQ-like queries. The results are similar to the one in our micro benchmark. Shard-based approach has very weak migration benefits because of high force contention. And our basic split migration increases performance by 1.5 times. And with location cache, the throughput is finally improved by 2.5 times, as 88% of remote access are reduced. So here's the conclusion. Location cache, locality is important and challenging for graph traversal. Traditional shard-based migration does not fit graph traversal. Our system Pragh uses split live migration. It supports fine-grained migration without metadata overhead. And our evaluation proves the effectiveness. Thank you for listening.
We have time for 2 questions.
Hi, Sam, no units. Can you say a little bit more about the coherency problem, the issue that you mentioned? How it affects performance and all that? The coherency.
Did you mean the concurrency of a location cache?
Yes.
Yeah.
The coherency, actually.
Coherency.
Because you bring the key into local, right? You make a copy of it, don't you?
Yeah. Yes. Oh, sorry. Yes, a location cache brings an inconsistency problem, and this is the common challenge for a location cache used in other systems. So we reuse the passive invalidation mechanism to solve this problem. And also, as our value will be reclaimed, so we also use list-based reclaim mechanism to solve this problem. Yeah, and if you are interested, we can discuss more offline. Yeah.
Any other question?
Have you considered how to deal with like load balancing issues? Yeah.
Do you mean the load balancing?
It means like, for example, actually, there are for certain kind of nodes, right? There are a lot of store some hotkeys, so there are a lot of like queries, maybe query certain kind of nodes, how to balance the nodes, make the whole query more scalable.
Yeah. Yeah, live migration can solve the problem of load balancing also, but our work is currently focused on to improve the locality. But Pragh is also can be also used to load balance. So, but we can't use it now. Just yeah.
All right, let's thank the speaker.
Thank you.